Welcome to Wednesday morning, CEDAR. And we have two presentations in the plenary today. I'm very happy to announce the next one. It's the second tutorial presentation by Gary Bust of APL. And it's entitled Ionospheric Imaging from Two-Dimensional Tomography to Data Assimilation.
Well, thanks, Tony. Thanks to CEDAR and the steering committee for inviting me to give this talk. I'm really excited and happy to give this talk, and I'm glad you're all here. What I'm going to talk about today is I'm going to start with just a survey of some of the tomographic methods and imaging and way things have been done in our community over the last few years. And when I asked people to give me some slides for some of these things and I started to look into it, I was just shocked at how much has been done and how much interesting things have been done. So I hope to kind of whet your appetite with that. And after I do that, I want to then talk about the fundamentals of what is this funny thing called tomography and try to go through the basic principles of it. And I will use large-scale radio tomography for that example because that's what I actually know best. And once I do that, then I'll move into the early work that was done in radio tomography back in the late 80s and through in two-dimensional tomography, and then from that go to 3D global GPS-based ionospheric tomography, and then finish off a little bit of what's the relationship between data assimilation, which we talk about a lot these days, and this tomographic imaging method. You know, what are the similarities and differences and how do they fit together? And then I'll just finish with some of the things I think that we could go forward with in the future. So here's an example. This is air glow looking upward from a plane that was done by basically at Illinois a few years ago. And here is horizontal distance as you're going through and altitude and seeing gravity waves as you go through here across this. So this is a pretty nice and innovative idea. You use a plane, you look up, and you do tomography to image the region of the lower atmosphere above you. So that's an example of things that have been done. Here's another one. We have a case where we have Guvi and Susie both who do these limb scans horizontally using the 1356 radiative recombination. And we have a case where these two instruments are not very far apart from each other, and we're seeing these different little maps in longitude, if you can see the degrees here at where they are at not too far apart in time, and we're seeing the ability to image multiple bubbles here going on. And of course, there's a lot more to that of the time evolution, but that's just showing, here's a case of using 1356 limb scans and looking at smaller scale structures and equatorial bubbles and the role that goes all the way through to forming small-scale structures that can interrupt communications and navigation and things like that. So that's an application of tomography. Going down that same path, this is a fairly recent result where we've taken Susie and Suli into IDA-4D. And so here is the Susie satellite on DMSP has the ability to recover its own electron density profiles through its own algorithm. This is what IRI kind of says is going on at this time. And then after you take in the data, this is what IDA-4D gets out, which if you think of IDA-4D as it's somewhere in between being a global tomography algorithm and data assimilation. So Suli alone, this is from Clayton Coker at NRL, and these are two-dimensional emission brightnesses you can see the magnetic latitudes here, and this is lower latitudes, and then down here, so since Suli is in the plane of the spacecraft as you're going forward, you can take multiple scans and put them together into a two-dimensional tomography inversion algorithm, which NRL has spent a lot of years doing and developing, and you can get out these two-dimensional reconstructions of the electron density, and then you can start to talk about what you think some of the physics is that's driving it. If you go back, one of the earlier things that was done was 2 or 3 receivers on the ground using 427 angstroms and 6030 or nanometers, 630 nanometers, and using the cross information from that to recover the two-dimensional structures in auroral latitudes. And here's the 4700 and here's the 6300 imaging, and you can see the altitudes here from about 100 to 270 kilometers or so, and then the horizontal distance and recovering those emission profiles. Now, something very recently that Josh Semeter gave me. This is a 50 times a second camera, and you're seeing this auroral breakup. And if you look at this region over here, this is near Poker, they put two cameras out, only 3 kilometers apart, because what they need to do is image structures that are only 100 meters wide and who will evolve on the timescales of a millisecond. And they are able to do that using new and different types of tomography methods that optimize for this problem. And then what they're able to do is to show that the precipitation and the average energy is changing as a function of time in altitude and the amount of energy you have. So that's brand new, that's pretty exciting, that's small scale, high resolution. And these are advances as time goes along that we learn new things and we go forward. Another way you can do this, moving to GPS, and I think a lot of you know that in Japan, they have a very, very dense array of GPS receivers. I think 1,000 of them over roughly the horizontal scales are a few tens of kilometers. When you look at a dense array of that and you're not looking at that many satellites, the problems in trying to get quality inverse images out of that are different from global tomography, so you come up with a lot of different methods to do that, and there's a lot of math on that in this paper about what's the best way to do it. And this kind of shows the grid they used, and then this is showing at different longitude sectors at one time being able to image these depletion regions. And then if you go back through the paper, you have other cases where they're able to show the time series of how those depletions grow. So that's a whole different thing from, say, the type of global tomography I normally think about. Very dense, small-scale structuring that you're trying to get in time. Here's one of my favorites, Paul Bernhardt, who is, without question, has some of the most innovative ideas for how you do things and manages to get them done. So he wanted to do tomography on a rocket to try to study sporadic E layers. So if you think about how hard it is to even image sporadic E layers to begin with, you have to have a lot of moxie to decide you're going to do that type of problem on a rocket. But this is over here is a simulation of if you had 3 receivers on the ground, what you could recover in the reconstruction. And then this is the actual case they did on the rocket where they only had 2 receivers, and this is what they finally got when they went through all the imaging. And they do get some structure down here. So that's a pretty exciting thing that was done back in 2005, I believe. If you continue with Paul, he, of course, did the 2-dimensional tomography I'm going to talk about in a while early on and continues to do that. So this is a case where he has receivers, tomography receivers from Northwest Research Associates laid out in an east-west configuration near the equator in South America. And as you'll see later, they are able to collect 150 and 400 megahertz data from the CNOF satellite that's flying through at 500-600 kilometers altitude. And these are some of the TEC curves they get as they look through there from the receivers, a 3 and a 4 receiver case here. And then this is what they reconstruct. And you can see the various depletion regions going along here at different altitudes. And this is the in situ PLP measurements of density. And you can see there's a fairly good agreement between what is being reconstructed in the 2-dimensional tomography and the probe. And this is ongoing work and is being submitted to be published. But it's exciting because now you're talking about using these methods to try to image these depletion structures. And if you're talking about it equatorially with a satellite going by every 90 minutes or so, you start to be able to see the history of what's going on. If you think about global 3D tomographic imaging, that's been going on for a long time. This is from my colleague in the University of Bath and their MIDAS algorithm. And this is a 3-dimensional image of the storm-enhanced density feature as it comes up through the US over the pole and breaks off and produces patches over here in structures. This is from the big October storm in 2003, and that's pretty exciting. And there's, of course, science in that, but as a community, we are always doing science, and we're also doing service to the user community as a large. And if you think about the fact that up at these regions, there's a lot of reason to do HF propagation through these at polar cases. I mean, if you have these gigantic structures up at 600 or 700 kilometers altitude propagating across the pole, that's going to change your propagation environment a lot. So having these type of things available to understand that can be an important application to the community in addition to just understanding the science. Several groups are now working on doing plasmaspheric imaging. So when we put up LEO satellites now, like Cosmic, for example, and they have dual frequency GPS receivers on them, in addition to the occultations that we're somewhat familiar with, they have upward looking positive elevation angle at the satellites up there. And if you think of the satellites not really moving and the LEO satellite whipping by, this is kind of tomography in reverse. It's again upward looking tomography. And now you have GPS data that's going from the altitude of the satellite, maybe 700 or 800 kilometers, up to 20,000 kilometers altitude. And so you have the real possibility of imaging the plasmasphere. And we had various people do this with one satellite from CHAMP and things, and now we have, this is Romina's work that she had a poster on, is ongoing. There's work going on in England. So here is a model from the global core plasma model from Gallagher, and then after the inversion in 2009 when she took in some cosmic data and Grace and Saxe, here's what we get out in the equatorial plane as the inversion. So that's ongoing and being developed work to try to image the plasmasphere, see if we can validate it and it makes sense against what people have been doing for years. And then that is another interesting both for science and plumes and things like that. Kind of the last one I'll talk about in terms of the survey. This isn't it's not been done, but it was a concept mission of doing magnetosphere constellation and tomography. This is the reference if you want it. And so here's their simulation. It's hard to see, but here's the Earth, and then they have a ring of satellites around it, and these satellites are all talking to each other using Faraday rotation. And then from that type of information, you reconstruct the magnetospheric plasma density. So maybe that is something in the future as we go. In this survey, I've tried to go from the smallest scales of 100 meters and milliseconds out through dense arrays to the global ionosphere, to the plasmasphere, and now maybe the magnetosphere. So this is an incomplete survey, and I apologize if I missed anyone or anything, but to me, it sets the stage for what's kind of exciting, and I'm going to say this again in the conclusion. This is our community. We build instruments, we build new instruments all the time, and we improve them, and we come up with new ways to do them. We put them on satellites, we put them on balloons, and we come up with new methods to do this type of tomographic imaging. So this is just an exciting part of our overall community. So what is that beast tomography? So I want to say at this point, my colleague in Bath, Professor Mitchell, gave me several slides that she's used as tutorials for her students on tomography. So when you see the blue title up here instead of white, that means it's her slide, so I don't have to say it every slide, just to let you know. So here we go. There's your cat going into the CAT scan. And here's the image of it afterwards. That's tomography. You put it in there, and you have data go from all angles, and you get an image of what's going on. And then down here, here's the ionosphere. We've got a fast-moving satellite, maybe at 1,500 kilometers. It takes maybe 20, 25 minutes to go across the sky. We've got several receivers on the ground, 3 to 10, and they're all getting these integrated measurements through the ionosphere, which is the total electron content, the integration of the electron density along the path between the satellite and the receiver. And you can just see visually, if you broke this up into little voxels or pixels, and you had enough data going through here, you ought to be able to do something, some type of weird methodology and estimation to pull out what the electron density is doing as a function of altitude and horizontal distance across here, a tomographic image. And it's the exact same principle as what was done in the medical community. Okay, well, let's just try to make the problem a teeny bit simpler. Here is our image we want to be able to get from tomography, and we've got just 2 horizontal cells and 2 vertical cells that we would like to know what is in there. It could be anything, but it could be electron density. If we could break up the US into just 2 horizontal pixels and 2 vertical pixels, we'd probably have a lot better chance of figuring out what's going on than by breaking it into thousands of them. So how are we going to do that? The essence of tomography is to try to figure out what's going in there without actually going in and measuring it directly. You measure it on the boundaries. And if you want to think about it, that's tomography. You've got a medium, you want to know what's going on. You can't or won't, or you just refuse, or you're not allowed due to invasion. You can't go into the body. So you measure it on the boundaries of things that penetrate from one side to the other, and you try to recover what's going on inside. So you take the measurements. 2 vertical here, 2 horizontal. Well, that should do it. We've got 4 measurements. We've got 4 unknowns. And these are integrated quantities across there. And in this case, she's saying, let's just assume that what we got was 10 every way. So no matter what direction you got 10. That could mean that maybe each of these things have 5 in them. That would be an example. So is that enough information? Do we now have a solution to tomography? 4 equations, 4 unknowns, but unfortunately not. There's a lot of things different ways that you could put values in those 4 boxes and come out with 10, no matter which horizontal and vertical direction you went there. And it's because the measurements were not all linearly independent. So even though you took 4 measurements from different directions and things, they're not linearly independent. So this isn't quite good enough. Okay, well, and the case we get most of the time is we don't have a lot of choice over the geometry. We still want to know what's going in here, but we've got a problem. This was our choice. These were the instruments we had out. This is the satellite that went by. This is the data. And we don't have, especially in the ionosphere, the ability to just go put a receiver and a transmitter at about 300 kilometers and have them just sit there forever while we take measurements back and forth. So if we can't change the geometry and the problem's not uniquely solved, then we need to have some type of prior information about what's going on. If you did have, say, a satellite with an in situ measurement on it whipped through, you might be able to know what one of these pixels is. Or if you know a relationship from physics, a physical constraint, that it's 4 times the other value. Or if you happen to know that your medium should be smooth, so you can put a constraint on that. But you put something on it that takes it from an indeterminate problem where there's a lot of solutions to one problem that gives you a unique solution. And just to kind of pre-do all this, what's the issue here? Well, your solution doesn't now just depend on your data. It depends on what you pick as the prior information. And picking different prior information can give you different solutions. Even though you're saying they're unique, that's great. If the prior information wasn't a good representation of reality, you've got a unique bad solution. So that's kind of the issues of tomography when you get down to it. Well, what if you can choose the geometry? That's wonderful. Instead of having them all go up, we'll put one go right through here on this angle where we just get one. And you can see that that's going to be pretty much the same as being able to estimate that pixel along. And now you really do have 4 equations. They all still are getting 10 going vertically, so this one's getting 5 times 1.41 along. So we get all the measurements on the right, and we can set up a linear equation where these objects here, these multipliers, are the length of each ray through each pixel. And we're just going to take the case where up and horizontal is 1. So if you work that out, you got 1 is equal to 1 is equal, and all this, and you end up getting a unique solution if you have enough measurements from enough angles. But going back, just to point out here, this is great if this was the boundary of your object. That works. In the ionosphere, it extends on. So we can't just say, oh, well, I'm going to take a measurement that goes through that lower pixel and ignore everything else, because it extends on. And in fact, if this is the ionosphere and if you're going up to GPS, it extends on up here. So we have another problem in our area where we don't have a bounded problem. We generally don't. So it's a lot easier if you want, well, not easier, but sometimes it's better if you have a structure you want on a smooth background. Okay, so that's our introduction to what tomography is. So that's the game. You're taking measurements on the boundary. You, for the most part, do not have enough control over your measurements to be able to guarantee that you get a unique solution out of the problem just from the measurements. And that means that you have to add some type of prior information to get a unique solution. And it would probably be nice if you could try to make that prior information as physically realistic as possible so that when you do get a unique solution, it's a good solution. So we go to two-dimensional tomography. Here's our satellites whipping across again. Here's our slant TEC as before. And here's the measurement. You measure what's going on across here, and it's the integral of the electron density along that path. It has some random error with it that's generally small, but it also has, and I'm thinking of two-dimensional tomography now, a constant of integration that is a separate constant for each receiver, because the receiver picks the satellite up over here, and then it tracks it as it goes across, but it doesn't know what the TEC was when it first picked it up. So you have a constant of integration for two-dimensional tomography that's different for each receiver. If you take all these different data sets from all the collected as it goes by, each receiver might collect 1,000 measurements and put them together into a gigantic array. You can get your data on the left. Your X now is your unknowns. Maybe you've broken this ionosphere into pixels, and each X is a pixel value of density, and then your H is that matrix that relates those pixels to the measurements, the forward model in the tomography problem. And quite often it's just the length of the whole ray through that pixel if we have a nice linear, non-curved type of tomography problem. So what are some of the problems? Well, you can just see limited angles. I mean, we have limited angle seismic tomography. We have all kinds of limited angle problems. We have the unknown constant that we have to address for each receiver. Oftentimes, we have less measurements than unknowns. I mean, if the ionosphere is very, very structured and you need to lay down pixels horizontally every 50 kilometers and every 10 kilometers of altitude, you may not have enough measurements. As I said earlier, the data is not linearly independent. If you could imagine that this wasn't curved at all, that was completely flat, and there was no horizontal structure at all, everything was only vertically, then the only independent information you would have would come from one ray. Everything else would just be dependent on the angle you gave it at. So in actuality, for our problem, the more structure, the better in some ways. It gives us independence in our information. This is a fun one for two-dimensional tomography. This is a pretty picture. But you know, you've got your array and the satellite's over here. It's coming like that. Or it's over here because you only got 4 or 5 satellites a day and you want to use all the data. Even if you do get it right overhead, the stupid Earth rotates underneath you during the 20 or 30 minutes you have it. So it's not straight, it's going like this or something. So you have to take that into account. And of course, it's surprisingly enough, most people don't want us to put our receivers on their roofs any place we want them. So despite the fact that we'd like to pretend this is on a line, you know, you've got it over here, over here. So you have to take all of those things into account, and they all lead to errors. So these are the things we need. The more diversity, to the degree we can control the geometry, we want to. And we need the a priori information that's going to go on here. So what about the constant of integration? Well, there's a lot of ways we did this in 2D ionospheric tomography. One of them is you can just add the constants as unknowns. And that's a real good idea, especially for modern algorithms. But the very first algorithms that we use that I'll talk a little bit more about, called ART and MART on the next page or two, the way they work, they don't really like having unknown constants of integration in their problem. They want to have absolute known TEC, so it wasn't easy to do that. You can estimate them from a separate technique. Multi-station Leininger method is one of them that's been used in two-dimensional tomography for years. The limitations of that is now you're going to assume a simple model of the ionosphere to try to estimate these constants, and that may or may not be a good method. You can just use the differential of the relative data. Just subtract the initial one off from the rest. And now you're in relative data. You've gotten rid of that constant altogether. But of course, you don't have quite as much information when you're looking at difference data. And that can be a problem. But that's been used quite often and a lot. The 3D geometry problem, well, believe it or not, you take your rays and you project them into a plane. That's what you do for two-dimensional problem. That's the way it was done at the start, anyhow, when you didn't have any 3D information. A little bit later on, you might have said, well, I'm going to make our pixels wide enough to take the off-diagonal thing, which is kind of the same thing you're doing. Something I didn't mention, but in the two-dimensional tomography problem, and it applies to a lot of data, the data is not beautiful and great. In our case, we have what we call cycle slips, where you've lost lock on the phase, and all of a sudden a big discontinuity partway through your pass. And you have to find them and fix them or get rid of the data. And back in the early days of tomography in the early 90s, graduate students, many of them went to insane asylums, and we lost them permanently because they would have to sit in front of computers all day long, manually looking at these things, finding them, and trying to fix them, and it was just too much. No. But that was an issue, and the point of that, the reason I'm saying it, is no matter how advanced our methods are, all the way to data assimilation, quality control on the data is a big thing. And it's surprising. You would think if you have 5,000 data points and just a couple bad ones get through that it's not going to matter. But it's almost the other way around. The bad ones drive problems in the solution. So quality control in the data is always an issue. And yeah, sometimes you sit there and you go through GPS receivers, 100 or 1,000 of them for a day, just to look and make sure that which one is the one that actually had everything 3 times higher than all the rest, and get rid of it. So it's still an issue. So this is some of the earliest things that were done back in the late 80s, early 90s, something called ART. And you start with some initial guess for an ionosphere, and you add corrections. J here is a pixel. So you've as many of them as you have in 2 dimensions you have. This is the iteration. The iteration is for each ray. You just keep taking a ray and you add this correction based on the data. This is the length of the ray through the pixels, and this is all of them. And you have a relaxation parameter to decide how much you're going to add this on. And you just keep iterating and iterating and iterating until you feel like you've got a convergent solution. And it's a fairly straightforward algorithm to implement, and for a lot of people, it's the first algorithm they implement in tomography. And it actually can be shown, I don't know that I could, but better mathematicians than I can show that it does converge to an optimal solution. So that's a lot of the places people started, but there's a lot of issues. There's nothing in this algorithm to stop the densities from going negative at all, and it does a lot of the time. It turns out that you're actually weighting this by the rays along a certain path, and if certain ones matter more than the others, you'll get artifacts that go along the rays. The relaxation parameter is arbitrary, and of course, you have an initial guess. That's your a priori information you've done to make the problem unique. You're starting off with something, and you're correcting it with the data that way. So another one that was used was MART, multiplicative algebraic reconstruction technique, I guess. And you start off, it's the same thing. Here's your initial ionosphere, but you're multiplying by this type of things. And this is, again, my math is a bit weak, but this comes from a family of maximum entropy solutions. And at least now you don't have negative densities, but the initial model is very important. And actually it turns out, because of this multiplicative factor, you'll get really strong striations along rays that look like field-aligned structures at times that aren't. So you just have to be careful. And that might be another thing that I didn't write down anywhere, but you have to keep in mind when you do these techniques and you put in prior information and stuff that you may see things that look real that aren't. And it's just part of the problem of the whole area. Other schemes. One that we used way back at ARLUT back in the 90s is we started off with a linear basis set of models, say from IRI, and used the data set to choose the coefficients of those models and put them together as one background model we started with, and then we did MART on top of it. It was okay. There's linear matrix inversions. You don't have to expand the density in pixels. You can expand them in basis functions. A lot of people have used these things called empirical orthogonal functions to get the vertical structure, and then they'll expand in Fourier series or spherical harmonics horizontally. And then your goal is to fit the coefficients. And if you think about that within the context of prior information, that's the prior information you've just used, where you truncate that basis set is how you make the problem unique. And then you can use a variety of things, but singular value decomposition to get the solution. And you can add on other regularization constraints afterwards. And in fact, a lot of work was done many years ago, and a PhD that came out of Finland by Femmers, I think, where they actually just set up the problem properly with regularization constraints from Tikhonov regularization, positivity constraints, other data sources you could put in to fix the solution, and went through it all. And so this is kind of where the whole 2D world ended up going to in the mid-90s or so. So I'll show you a couple examples. This is one we did in Greenland in 2002 under an NSF grant, which was really, really a great experiment we did with the Danish Meteorological Institute and Jürgen Waterman. And we had 4 receivers starting down at Narsarsuaq and going all the way up past Sonderstrom, and 1 at Sonderstrom, so 4 tomography receivers. And then this is a particular case where we got the TEC data. And so this is latitude here. This is the TEC, slant TEC values going up here, and we had 3 receivers for this case. And what you can see is the bottom number is 0, and that means it's relative. We didn't know what the constants were, so we just made it positive. And you can see all the structuring we had here. And so this produced our tomographic inversion algorithm, and we had scans of the SuperDARN incoherent scatter radar at the same time. So the colors here is the scan of the SuperDARN radar going along the north to south direction, and the contours is the overlay of our tomographic results on it. And it's a pretty good fit for this one. I wouldn't show you a bad one. I'd show you a good one. So, and it's in the paper. But what Jürgen did, which was just brilliant, we had about 7 of them or so during the day. And what he did was he just manually moved these contours back and forth and up and down till he got the best fit to the incoherent scatter radar he could get. And then he looked at how much he had to shift it. So for 2 of them, he had to shift them up by 30 kilometers. 2 he didn't have to shift at all. 2 he had to shift down by 30 kilometers. And he had to shift some of them right and left by 30 kilometers. So you could argue, even though this is a manual, small statistics type of thing, that the spatial accuracy we got horizontally and vertically was about 30 kilometers. So that was a nice little experiment that was done. Another famous one from this time was again from Professor Mitchell in 1995. And this is the tomographic image. Now it's IceCat, and you can see the trough represented very well, the low latitude structure, this poleward blob structure right on the other side of the trough that shows up there. Even this down here seems to show up a little bit. So it was a very, very nice reproduction of the incoherent scatter radar. And it's these type of things that gave us a lot of hope that tomography actually could be used in the real world for science. I should say that when this particular result was first shown, people had trouble believing it, and they thought that somehow the ISR information had been taken in to create this image. It was just that surprising that it could do that well. So that's 2-dimensional tomography, and this all went on from the late 80s and continues on. We just, I guess in the student session, and we heard yesterday in Sabani's session, putting satellites and then receivers on planes in Canada and doing 2-dimensional tomography, or maybe 3-dimensional tomography. And like I said, Paul Bernhardt's still doing it. So this type of imaging area continues on. However, there were some issues with this. Particularly, there were issues from scientists and applied people. They didn't seem to like the fact that you could only get a 2-dimensional image in a little region rather than a spatially distributed region that might tell you a lot more about what's going on. And they didn't particularly like the fact that you only got an image every 2 or 3 hours. I don't know what was the matter with them, but they seem to indicate to all of us in the community that perhaps we should think a bit bigger. And so we thought bigger, of a global imaging, and a lot of groups, and I'm not going to mention them all by name, started doing this all at about the same time. And of course, the primary data set that you can use globally, the one that's available, is GPS. It's all over the world, and it's TEC, and we already know how to do it. I like this picture because it shows the reality of GPS. The data is very sparse. It's a problem. So we went to the fact that you have data available everywhere on the globe from GPS receivers, and thank goodness freely available for the most part. But now we have a problem that there's just large regions where there isn't any data, and I'll go into some of those things a bit more. And another cartoon showing the data and how you would do the image, but now it's three-dimensional. Not only do you have this, but you've got this profile going here. And of course, now we're back to the same problems, which is why I introduced it with the two-dimensional and even back with the boxes. It's the same problems. We've got now a three-dimensional ionosphere. So if we do pixels, they're now voxels, latitude, longitude, altitude. We have to think about what it means to go up to 20,000 kilometers at least. And we've got sparse data with limited angles, and it's the same problem of what do we do for the prior information. And so here's some of the issues. So GPS-TE has receiver and satellite biases. These come from the fact that you've got two frequencies being, say at the satellite, being generated coherently and then coming through different paths electrically out through the antenna so that by the time they get into space, they're slightly offset in time. And that offset, a few nanoseconds, leads to a large error in total electron content. You have the same problem when it comes at the receiver at the end. And of course, with the receiver on the end, if it's not really at a site that's being well managed, you might have someone just decide to, I don't want the antenna there, and move it somewhere else or bring in their electrical equipment or something. So those values can change over time. So that's an issue. It was really great when the LEO tomography whipped across the sky in 20 minutes. I mean, we used to think at the start that, oh, the ionosphere's got to be static for 15 minutes. That's such a constraint. Well, gosh, GPS takes 6 hours to get across the sky. I mean, would that we had as many LEO satellites in the constellation as we do GPS. So you have to deal with the fact that GPS doesn't move very fast. And each GPS receiver typically only sees 10 to 12 satellites or so. And it's not uniform geometry. The GPS only goes up to 55 degrees elevation. So it's not really great. And this leads to the fact that it's just a mixed or underdetermined problem. So below here, I want to take a few minutes to just talk about some of the methods that have been done to deal with this. The first one is to use JPL, or there's other people, but I'm just going to mention them because Tony's sitting right in front. The estimate of the satellite biases, and they've been doing this for a tremendously long time, and they're good, and they've got it stable, and I think they would probably argue that it's better than less than one tech unit, maybe down to a half or something like that. And so that seems like a reasonable thing to do, that you use those values, you subtract them off, and your residual error on the satellite biases is pretty small. It's a little bit harder to calculate the receiver biases. Again, JPL does this for a set of stations and all the time. But I think by and large, there's stations that they tend to use in their maps all the time, and there's stations that come from quality sites where we know something about what's going on. So it's a little bit harder if you're going to just bring in, as we sometimes do, data from 4,000 GPS sites globally, and you have no idea of where they are or how they're sited, to estimate those receiver biases when they could potentially be changing as the day goes along. But you can do that separately. You can do it as part of the imaging solution. They're just unknowns, and if you've estimated the satellite biases, you add more unknowns into the problem that you have to estimate, and you can decide that you only have to estimate them once a day or once every few hours or however you want to do that. You can use relative TEC from each receiver. You can use a satellite as a reference and subtract it off, and if you use all that difference data, you've gotten rid of the receiver bias to the degree that the receiver biases are independent from the satellites, which is another ongoing issue. You can use the phase arc difference, much like we did in two-dimensional tomography, where you only use, for a given satellite receiver, you look at that change in TEC as it goes across the sky, but now you're explicitly in a time-dependent algorithm because you have to actually use those differences and somehow account in your solution for a time-dependent solutions. But those are some of the methods that have been used to try to deal with this problem. And I'll just say that I think we all feel this is an ongoing issue. If you would like to get, just in terms of TEC, your residual TEC errors down under 1 tech unit or lower, which is one of the things that allows you to get accuracy on problems to better than a cycle, it's still an area of research. Time dependence. Well, we do have, just based on this face, when we have time-dependent algorithms, maybe you have a window of 6 to 8 hours or moving forward with 30 minutes updates, and you just solve for the ionospheres every 30 minutes all the way through there so that you can use the phase arcs and get highly precise information, and you also can take that into account in time. A lot of us use a Kalman filter to move forward in time, and that helps. I mean, you use the previous solution from 15 minutes ago. Maybe it was sparse, and maybe initially you didn't have great results, but now you keep building on that, and eventually, if you do the problem right, you get a nice solution. And then you have the possibility of taking your results and putting them back into a full physics model that can predict forward in time for you, and that will help a lot. So those are some of the time dependence methods. The sparse data. Well, again, you can expand in basis functions. That's a way to deal with that. You can have a background model or a forecast. That's a prior information. You can use regularization, and you can use other data sets. Notice that it's not like we have any really new methods of dealing with the prior. They're the same methods that was in the two-dimensional tomography. Now it's a three-dimensional time-evolving problem that we deal with. The background model forecast fits into the data assimilation I'll talk about in a little while as being one of the things that can go on. Okay, so my algorithm is IDA4D. I use the Gauss-Markov-Kalman filter to go forward in time. I use the relative GPS to get rid of the receiver biases, and I use as much data as I can possibly get, oftentimes without being able to do the quality control I need to on it, but allows me to look at things. This is an example, fairly recent, October 2011, and you can't even see it, but I mapped the electron density at 300 kilometers that we got out after running the algorithm. But then I took an hour. I do it at less than that, but just to give you a sense of what goes on over an hour. And all the orange little fuzzy motions are the 300-kilometer intercepts of the ground GPS data as it's moving across the sky globally. So that's what you have. The yellow lines are kind of a representation of the LEO satellite and then where an occultation pierces the ionosphere to kind of give you a sense of the spread of radio occultations from cosmic and other satellites going in here, while the dashes are the upward-looking TEC above the satellites. The reds, which don't show up very well, here, those are Doris receivers on the ground, and those are the TEC that they saw as satellites move through here. So I didn't use any ionosons or any other in situ data. And that's the type of coverage you can get here. And in some ways, it looks really good. And in some ways, there's no data. So this is the kind of things that you can use in algorithms today to do imaging of the globe. Here is an old result from 2001 that I did with Jeff Crawley. Well, we published it in 2007, where we took the tomographic IDA4D solutions and looked at the maximum density, the NMF2, over the polar cap. So that's what all this red and yellow is. And you can see a tongue of ionization going through here, and you can see maybe some break-off over Canuck and the plasma going around. And these are the potential patterns that Jeff got out from Amy for the same time period. And there was no use of Amy in my algorithms. The algorithms were completely independent and separate. So one of the nice results of this was how well there was a matching between the flow in what we saw in the imaging and the potential patterns. And then we did a lot more with that. This is kind of an example to give you a feel that this type of imaging can be done for science. And I think there's a lot more examples I won't go into, but you have to believe the images. You have to have a feel for their accuracy or what they are, but you can do things with them then. This is a movie from November 20th, 2003, which, as most of you know, was one of the two gigantic superstorms from that time period. So I am visualization challenged, so I don't really have beautiful three-dimensional plots of things as Catherine did from Midas, but I saw what JPL did at one time where they stacked these, and I thought, this is a great idea. And then basically Astra and the people there developed all this software, and we stacked these at basically 300, 400, 500, and 600 kilometers altitude. And you can see as time goes on, if we run this through again, that we start off with most of the density in the morning over here at about 300 kilometers altitude. Here it is. This is where the density is as you're going along over Asia. As you're coming in, this is noon Well, actually, it's the afternoon. Here's 12 noon. Here's 15 UT. And here's the real time up here. And, the storm started about shortly after a UT of 12 or so is when it really started to hit. And you can see you start getting plasma at higher altitudes. And by the time you hit a little bit farther over here, this thing is going to distribute itself all the way up through at least 600 kilometers altitude. And this is results that Xiaoxing P were showing yesterday too for similar cases. And you can see it go across. And there's as much density at 600 as there is at 300 in this particular case. So again, you can start using this for science depending on how much you believe it and stuff, because you want to ask what was the physics that lifted that plasma up that high, what transported it across the pole, and where did it eventually go. And so you might say, well, it's the E cross B drifts that lifted up, or you might say it's the winds that lifted it up. Or maybe there was a change in composition that was what really did it. So those are things you could start to address with these type of things. As we get better and better and better at believing our global images, we can scientifically talk about coupling between equatorial, mid, and high latitudes and some of the processes that are doing them on these global scales. Okay, so I want to finish in the last few minutes of talking about data assimilation a little bit, because it's kind of the natural next step. But there's kind of two ways you can look at it, at least the way I look at it. There's data assimilation from the tomography point of view, and there's data assimilation from the data assimilation point of view. So from the tomography point of view, the primary goal of what we just showed there with those images is accurate estimate of the global electron density field on some space-time resolution thing. That's what we want to do. We're not even really that concerned about prediction at this point. We'd like to get these estimates correct. And as I've tried to convince you, what we need is a priori information to be able to regularize and get unique solutions from our data. So to that degree, data assimilation is one method of getting the a priori information. You take your images you got out, you run them through something, a Gauss Markov or whatever, you get a better forecast than you would if you just used IRI. So you've got a better starting condition, which means you can do a better job on the data. The error covariances that you get out of this allow proper weighting between the data and the model. That's a nice a priori information. Oh, exactly over what spatial regime should this data apply? If I have really good data in the US, can I say that I understand what's going on in Asia? So that's another, and what's nice about this is physics. I mean, we have the hope someday of getting this right. So you have the hope of not having a priori information that you just pulled out of your back pocket because you thought it made sense. So I do like that because of that. But the goal is this. From data assimilation, the primary goal is to improve the models. You want to have a model that can predict the state of the ionosphere and the thermosphere, for example, accurately for a variety of reasons, science and applications. And the purpose of the data, any data, whether it's tomographic data or anything else, is to help the model, to nudge it in the right direction, to improve it. So from a data assimilation point of view, tomography and what we've been doing here is just one of many ways that you can get data into a first principle model and help correct it. And the goal there is how well do the observations improve the model predictions. I mean, we've heard about this quite a few times here, but there are reasons, societal reasons, to be able to predict things 6, 12, maybe 72 hours in advance. That's a function of trying to get models that can predict that, and the data is used to help them do that. At least that's kind of my view on that. Here's my little cartoon of a data assimilation cycle. You have the observations over here. You've got the analysis of some, generally not all, of the state variables, which is what was tomographic imaging and still could be. But you could potentially take in wind measurements and other things and get an analysis of those. Then you might, there's other ways to do this, but you might reinitialize based on that some of the state variables, maybe try to get consistency on all of them. Feed that into your first principle model. And here's the part that is the tomography. Oh, good, wonderful. I've got a short forecast of the next analysis time. I can do a better job of analysis and estimation of my results. And then you have the longer one that says, oh, okay, here we out here in space weather applications. We've fed all this stuff well, and we're able to predict 6 hours in advance or whatever. And these little things in here, they're nice, pretty boxes, but big, giant research area, right? Big, giant research area, big, giant research area. So a lot of work that can be gone on here inside these pretty boxes. Well, so I think, and I hope I've convinced you over this, that this is an active field. There's a lot of things we can do with it, and I think there's a lot of future work. We're just starting to touch these mesoscale, small-scale tomography imaging, the things Josh showed, 100 meters, milliseconds. That's pretty amazing. Dense arrays. You know, we have dense arrays of GPS in California and in Japan and other things. And we have other types of dense arrays. We have the possibility of having dense arrays of imagers. I mean, these are possibilities. We're doing satellite imaging of small scales more and more often when we look at equatorial bubbles. We keep coming up with new measurement types to do tomography with, and they all require optimal methods. There's a lot of math and understanding. I mean, I think the point has been made more than once. You take your resolution in space and time and the problem you want to solve and the type of data you have, and probably you need to define a new optimal estimation algorithm for that problem. You don't, it's not, the global algorithms I've been showing, the methods there probably don't work on the scales of 5 kilometers to 100 kilometers. New platforms. I want to just pull out and mention suborbital. There's going to be a workshop in this tomorrow, commercial suborbital. So we saw rockets. What a wonderful thing. We can now maybe put these type of tomography systems on a plane that will go up to 100 kilometers and be up there for 4 or 5 minutes and come back down and do it every 2 hours. So I think there's a lot of things that can be done here. And I just want to say CEDAR is a great community for this. We build instruments, we deploy them, we put them on balloons and rockets and satellites, and we put them in the equator, and we put them in the auroral region, and we've got the theoreticians and the mathematicians and the estimation people to be able to do the inversions, and we've got the models we compare to. I just think it's a great community to do this, and I'm glad to be able to give this talk. Finally, I want to do some acknowledgements. A lot of people have worked in tomography, and I didn't credit everybody. I just skimmed over the top, but you can go back and look. But I want to pull out Jeff Austin, the University of Illinois in 1988, who wrote the first paper on this, and unfortunately didn't stay in the field, but was that innovative idea that at least got me going, and I think a lot of other people going on. Data providers. I mean, most of us, I use data all the time, and we take it for granted. We take for granted where we get the data, that someone paid to put these instruments out here, paid to put them on the web, came up with standard methods like Reinix of representing them, sometimes doing data quality. So this is an important area that goes on. I want to personally acknowledge ONR, and specifically Bob McCoy. In the late 90s, he continued to fund me and allowed me to develop from the two-dimensional tomography to the global IDA 4D I have today. And I think if I hadn't had that support then, I wouldn't have been able to continue on. So I really appreciate that, as I do NSF. I've just put out 2 grants that were more relevant to this, but it was a great thing. All of my organizations I've worked to, and this is why I like our field. I mean, they've let me do what I want to do. They've put up with my whining, and it's great. It's just fantastic altogether. And finally, you know who you are out there. It's a good thing to be able to do what you like and to have fun doing it with your friends and colleagues, and it makes it all worthwhile. And to all the young people here, that's what I say, have a good time and enjoy it. And thank you very much.